everyone, today we're going to be studying the topic Mass Spectrometry from Edexcel AS Level Chemistry Unit 1. Indeed, it's a little tricky, but I'll try my best to explain it in such a way that it's easy to understand. Atomic mass is the average mass of an element's atom, considering the relative abundance of its isotopes compared to 1/12 the mass of a carbon-12 atom. You need to memorize this definition. You might not understand it now, but you will understand once we dive deeper into the concept. So mainly it's a weighted average of the element measured in atomic mass units, and it's mentioned in the periodic table for all elements. If you remember from the previous video, I had explained about isotopes and mass number of an element. Quick recap: isotopes are atoms of same element, which means they have same proton number but they have different neutron numbers. An atomic mass being the number of protons plus the number of neutrons. Here's an example. We have chlorine 35 with an abundance of 75.77% and chlorine 37 with an abundance of 24.23%. To understand it easier, let's say I have a basket of apples. 75.77% of apples weigh 35 grams and the other 24.3% weighs 37 grams. Although both are same fruit, which means they are of the same element, but some have different mass, which means they are isotopes. And when we calculate the average mass, considering all of the apples, their weight and their abundance, we get the atomic mass. To calculate the atomic mass, we use the formula on the screen. We multiply the mass of the first isotope with its abundance, then multiply the mass of second isotope with its abundance, then add both the answers. Finally, divide by the sum of abundances, which always sums up to 100. If it's not adding to 100, then there's probably something wrong or you missed something in the question. Go back, read it again. And when we apply this formula for chlorine isotopes, we get 35.45 as atomic mass for chlorine, which can also be seen in the periodic table. Isotopic mass is the mass of a specific isotope of an element compared to 1/12 the mass of a carbon-12 atom. Okay, so this one is different for each isotope within the same element. The atomic mass was the average of all isotopic masses. We calculated using mass spectrometry. As you saw earlier, we had chlorine 35 and chlorine 37. 35 and 37 are their isotopic masses, which are used to calculate their average atomic mass, which is 35.45. Relative molecular mass, symbol being Mr, and relative formula mass. Both of them are the sum of atomic masses of all atoms present in the molecules. The difference is Mr is used for covalent compounds and RFM is used for giant lattices or ionic compounds. As you can see in the table, we have some examples. Mr for H2 would be 2. As I said earlier, we need to sum the mass of all atoms present, even if it's the same element. Mass of hydrogen is 1. If 2 atoms are present, then Mr of H2 would be 2. For ammonium sulfate, NH4 twice, and SO4, that means we have 2 nitrogen atoms, 8 hydrogen atoms, 1 sulfur atom, 4 oxygen atoms. Mass of nitrogen is 14. 14 times 2 is 28. Mass of hydrogen is 1, and we have 8 atoms, so mass is 8. Mass of sulfur is 32. We have only 1 atom, so that will remain as 32. Mass of oxygen is 16. 16 times 4 gives us 64. 28 plus 8 plus 32 plus 64 gives us 132. So Mr of ammonium sulfate is 132. So, what is mass spectrometry? Mass spectrometry is an analytical technique used to measure the mass-to-charge ratio of ions. It provides information about the molecular weight and structure of compounds. A mass spectrometer is the instrument used to carry out this analysis. So the basic idea is it tells us the mass-to-charge ratio of ions and their abundance, which we can further use to calculate atomic mass. It works by ionizing chemical species and sorting ions based on their mass-to-charge ratio, also known as mass divided by charge. The symbol can be m/z or m/e. I'll be explaining this further. The process. First, our vaporized sample would be ionized. If we look at the picture, we have an electron gun at the beginning. It will bombard our sample with a beam of high energy electrons, which will knock off 1 or 2 electrons from our sample, turning it into a cation. Usually it's a 1+ charge, but in uncommon cases we can have a +2 charge as well. Acceleration. Our sample passes through an electric field created by the charged plates which are labeled in the picture, and since our sample has a charge, they accelerate due to the electric field. Deflection. Our sample will be met with a magnetic field which will be produced by the strong electromagnet that you can see in the picture, and due to the charge our ions will deflect. Lighter ions will deflect more than heavier ions. You can see in the picture the blue dotted path is deflected more than the red dotted path, which means blue path belongs to a light ion and red path belongs to a heavy ion. Detection. Our sample's mass to charge and its abundance will then be detected and displayed as peaks on a chart. So why is it necessary for the sample to be vaporized and the process to occur under a vacuum? Ionization requires free particles. Solid and liquid particles are packed together and so cannot be ionized. Solid or liquid samples could clump together. Solid or liquid particles wouldn't be able to move freely through the electric field. And for vacuum conditions, if air particles are present in the mass spectrometer, the particles could collide with our sample, deflecting them the wrong way. And air particles would also result in unwanted peaks. Air particles could also damage sensitive parts of the mass spectrometer. Fragmentation. In mass spectrometer, our sample, if it's a molecule, will also go under fragmentation. The mass spectrometer will break our molecule and form peaks for the mass of each fragment. Over here we have example of ethanol. We have a couple peaks here. The peak with the greatest mass to charge ratio is called the parent ion peak or the molecular peak, meaning no fragmentation is done, the entire molecule is ionized and detected for its entire mass. The peak with the greatest abundance is known as base peak, meaning the most molecules of ethanol have been fragmented with the mass to charge ratio of 31. CH3 ion gives a peak at 15, CH3CH2 gives a peak at 29, and CH2OH gives a peak at 31. And all these peaks are visible in the spectrum. Sometimes the questions might provide you with peaks and ask you to find out what the molecule is, or they could provide you with a molecule and ask you to draw all possible peaks for this molecule. So you need to be well aware of this concept. Chlorine exists as two isotopes, 35Cl and 37Cl. A compound containing one chlorine atom will therefore have two molecular ion peaks due to the two different isotopes it contains. The ratio of the peak heights is 3:1, as the relative abundance of 35Cl is 3 times greater than that of 37Cl. A diatomic chlorine molecule, the one that naturally exists, will have 3 molecular ion peaks due to the different combinations of chlorine isotopes they can contain. The ratio of the peak heights is 9:6:1. This ratio can be deduced by using the probability of each chlorine atom being 35Cl or 37Cl. It's like in a box we have 100 apples, 75 apples weigh 35 grams and 25 apples weigh 37 grams. What's the probability you pick a 35-gram apple or 37-gram apple? Same concept. We have 4 combinations for diatomic molecules. If we have 2 isotopes, we can have 35Cl with 35Cl. We can have 37Cl with 37Cl. We can have 37Cl with 35Cl or 35Cl with 37Cl. Cl35 has an abundance of 75, as we saw in the earlier slide, and 37Cl has an abundance of 25%. 75% in fraction is 3/4 and 25% is 1/4. Hopefully you know the AND and OR rule from probability. For ANDs, we multiply, for OR, we add. For 35Cl and 35Cl, we have 3/4 times 3/4 gives us 9/16. For 35Cl with 37Cl and 37Cl with 35Cl gives us 2 times 1/4 times 3/4. We are considering these two together because they have the same MR, which gives us 6/16. Their peaks would be of greater abundance due to 2 combinations of the same MR. And for 37Cl with 37Cl, 1/4 times 1/4 gives us 1/16. Therefore, the ratio 9:6:1. It's also the same if we have 3 molecules of chlorine. Like in nitrogen trichloride, either all 3 chlorine atoms could be 35, or 2 could be 35 and 1 could be 37, or 2 could be 37 and 1 could be 35, or all 3 could weigh 37, meaning we will have 4 peaks. The first spectrum is of chlorine atoms. We have two peaks, one for chlorine 35 with the abundance of 75% and the other for chlorine 37 with the abundance of 25%. That's why their peaks are in 3:1 ratio. The second spectrum is for chlorine molecules. A Cl to Cl molecule, already has three peaks that are due to four combinations. The smaller peaks with less mass to charge ratio are of chlorine atoms. The molecule has been fragmented into atoms, so we can see the same 3:1 ratio peaks as we saw for the atoms only spectrum. Bromine too exists as two isotopes, Br79 and Br81, both with a relative abundance of approximately 50%. So a compound containing one bromine atom will therefore have two molecular ion peaks due to two different isotopes it can contain. The ratio of the peak heights is 1:1 as the isotopes are equally abundant. A diatomic bromine molecule, which is again the natural form of bromine, or a compound containing two bromine atoms will have three molecular ion peaks due to the different combinations of bromine isotopes they can contain. The ratio of the peak heights is 1:2:1, which can be deduced by using the probability of each bromine atom being 79 Br or 81 Br. 79 Br with 79 Br gives us 1/2 times 1/2 gives us 1/4. 79 Br with 81 Br and 81 Br with 79 Br is 2 times 1/2 times 1/2 gives us 2/4. 81 Br with 81 Br gives us 1/2 times 1/2 gives us 1/4. Again, 1:2:1 ratio. Pretty much the same concept, just different peaks and abundances. So as you can see, where we have bromine atom, we have two peaks of the same height, almost 50%, but for Br molecule, we have three molecular peaks and two atomic peaks. Three peaks being in a 1:2:1 as calculated earlier. This concept might get easier when we get to the question, so please tag along. Here are some more uses of mass spectrometry. Identifying unknown compounds. MS can determine the exact mass of molecules in a sample, helping identifying unknown substances. Forensic science, used to analyze trace evidence like drugs, toxins, or explosive residues in crime investigations. Analyzing space material. MS is critical for studying otherworldly materials such as meteoroids or soil from other planets. Drug testing in sports. MS can detect banned substances in athletes' blood or urine samples with high sensitivity. Pharmaceutical analysis ensures drug purity, identifies impurities, and confirms the molecular structure of new drugs. Isotopic analysis measures isotopic ratios of elements in a sample to provide information about its origin. Radioactive dating determines the age of samples like fossils by measuring the isotopic composition of radioactive elements. Biomolecule analysis helps identify proteins, lipids, or DNA sequences in biological samples. Let's look at some questions now. What is the correct definition of relative isotopic mass? The weighted mean mass of an atom of an element relative to 1/12 of the mass of an atom of the isotope carbon-12. No, that's wrong. That's atomic mass, not isotopic mass. The mass of one atom of an isotope relative to 1/12 of the mass of an atom of the isotope carbon-12. Yes, that's right. Mass of one isotope compared to carbon-12. So B is our answer. The percentage composition of the two bromine isotopes in a sample is given in the table. Mass of bromine 79 is 78.918 and abundance is 50.52%. Mass for bromine 81 is 80.916 and abundance is 49.48. Calculate the relative atomic mass of bromine in this sample. Give your answer to 2 decimal places. Alright, so if you remember, the formula for atomic mass is mass of isotope 1 times its abundance plus mass of isotope 2 times its abundance divided by the sum of two abundances, which is 100. Now put all the numbers in the formula. So 78.918 times 50.52 plus 80.9106 times 49.48 divided by 50.52 plus 49.48. You'll get 79.903. The question asks for 2 decimal place, so it will be 79.90. The mass spectrum of a sample of bromine molecules with approximately equal proportion of 79 Br and 81 Br isotopes is And we have 4 graphs. The question says 2 isotopes of Br with equal abundance. If you remember, a diatomic molecule will give molecular peaks and atomic peaks. In option A, we don't have molecular peaks, so it's not our answer. Let's look at all possible fragments or molecules. We have Br79 and Br81 for monoatomic ions. For diatomic, we have Br79 with Br79, mass being 158, Br81 with Br81, mass being 162, and Br79 with 81 or 81 with 79, so twice the height at 160. B has no peak at 160, so it's wrong. The peak at 160 is in option C is almost the same height as the rest, which is not correct, as we have 2 combinations for mass 160, so twice the abundance. So the correct answer would be D. Methanol and ethanol are both green leaf volatiles. There are a number of fragment peaks which appear in the mass spectra of both compounds, but somewhat surprisingly, the OH positive peak at mass to charge 17 is not one of them. Suggest the formula and mass to charge values of 2 fragment ions that you would expect to occur in both spectra. So first we have to draw out the displayed formulas of ethanol and methanol and try to mark the same fragments in both molecules. So as you can see, both share these 2 fragments of CH2OH plus with mass 31 and a CH3 plus with mass 15. Remember to put the positive sign because it's an ion. Give the formula 1 fragment ion that you would expect to be present in the mass spectrum of ethanol but absent from that of methanol. So again, draw out ethanol and methanol, compare and see what fragment is possible in ethanol that's not possible in methanol. Since ethanol has 2 carbons and methanol has 1, a fragment that contains 2 carbons will only show for ethanol. So as you can see, C2H5 can be made from ethanol but not methanol. Again, don't forget the charge. A compound which has major peaks with mass to charge at 29, 57 and 58 in the mass spectrum could be A. propanal, B. propanone, C. propane 1-ol, D. propane 2-ol. So first we have to draw out all of these formulas in their displayed form and label out their fragments. So as you can see, I've drawn the displayed formula of propanal, propanone, propane 1-ol and propane 2-ol and have labeled the fragments. The only molecule that gives peaks at 29, 57 and 58 is propanal. So our answer is A. A sample of bromine contains equal amounts of the 2 isotopes. Complete the mass spectrum to show the peaks you would expect for Br2+ from this sample of bromine gas. So in the question they are asking for the peaks produced by the molecular ions, so no need for monoatomic peaks. So let's write out all possible molecular ions. So peak at 158 for Br79 to 79 with abundance of 50%. Then a peak at 162 for Br81 to 81 with an abundance of 50%. And a peak at 160 with twice the abundance because there are 2 combinations. Because for 79 with 79, it will be 1/2 times 1/2 gives us 1/4. For 81 with 81, it will be 1/2 times 1/2, again giving us 1/4. For 79 with 81 and 81 with 79, it will be 1/2 times 1/2, which is 1/4. Then we multiply by 2, which gives us 1/2, giving us 1:2:1. A mass spectrometer was used to analyze a sample of oxygen gas in which the most abundant isotope was O16. The oxygen was ionized and the ions were accelerated by an electric field. Suggest the formula of 2 different ions containing only the O16 isotope, which might be formed in the mass spectrometer. Okay, in the question it says oxygen gas, and oxygen gas exists as a diatomic molecule in air, so let's write out all possible fragments of oxygen. So either we can have O2 with a positive charge or O2 with a +2 charge. We can also have fragments of a monoatomic O with positive charge and an O with a +2 charge. So you can write any 2. Which part of the mass spectrometer separates ions of different mass? So if you remember from the diagram of the mass spectrometer, we have an electromagnet that creates a magnetic field which deflects the ions based on their mass to charge ratio. For the 2 ions you have chosen, sketch their paths in the mass spectrometer after leaving the electric field and as they approach the detector region. Label each path with the formula of the ion. As we know, lighter ions deflect more than heavier ions, and I have chosen O2 with a positive charge and O2 with a 2 plus charge. The ion with a 2 plus is lighter than O2 with a single charge, so the path would look something like this. I hope you understand, and don't forget to label. A sample of an unknown molecule is analyzed using mass spectrometry. A peak is observed at mass to charge 42, corresponding to an ion with a 2 plus charge. What is the actual mass of this ion? This is pretty simple. We just multiply 42 with 2. So the mass is 84. Suggest a possible fragment or molecule that could produce this peak, assuming the molecule is a cycloalkane. So first we need to write down the general formula of cycloalkanes, which is CnH2n, which can also be written as 12n plus 2n, 12 being mass of carbon and 2 being the mass of 2 hydrogens. 12 plus 2 is 14, so 14 times n gives us 84. So n is equals to 84 divided by 14, which gives us 6. So n is equals to 6. The formula would be C6H12, a cyclohexane. A sample of magnesium contains 3 isotopes and has a relative atomic mass of 24.32. The table gives abundances of 2 of these isotopes. Calculate the relative abundance, hence the mass number of the third isotope. Give your answer to appropriate number of significant figures. So we have 24, 25 and a third unknown mass number. Let's call it X. And the unknown abundance A. The sum of all abundances is 100. Therefore 78.99 plus 10, which is 88.99, then 100 minus 88.99, that would give us the percentage abundance, which is 11.01%. Now if you remember, the formula for the atomic mass is sum of all masses times their abundances, then divide by the sum of all abundances, which is just 100. Now we substitute the known values. So 24.32, which is the atomic mass, equals 24 times 78.99 plus 25 times 10 plus X times 11.01 divided by 100. We shift the 100 to the other side, multiply by 24.32. Now it will be 2432 equals 1895.76 plus 250 plus 11.01 X. 1895.76 plus 250 is 2145.67. We will shift it to the other side and subtract it from 2432, which will be 286.24. Now we divide it by 11.01 to get the value for X. We get 25.99, round off to 26. The mass spectrum of propane 1-ol is shown, which peak represents the molecular ion for propane 1-ol containing a carbon-13 isotope. So first we draw out the displayed formula of propane 1-ol and label the carbons with their mass. And the question says one of them is carbon-13 instead of carbon-12. So as you can see here, the total mass is 61. So our answer is D. Bromine has 2 isotopes, Br79 and Br81. The presence and abundance of these isotopes can be determined by using a mass spectrometer such as that shown in the diagram below. Explain how ions are produced in the area labeled A. So if you remember, the first step of mass spectrometry is ionization. The sample is bombarded with a beam of high energy electrons by the electron gun, which knocks off electrons from our sample. State what is used to deflect the ions moving through the mass spectrometer in the area labeled B. If you look at the picture, B is the region where deflection occurs due to the magnet field produced by the electric magnet. Explain why there is a vacuum in mass spectrometer. So this is pretty simple. Air particles can collide with our sample and interrupt their deflection from their respective paths. How many molecular ion peaks, which means parent ion peaks, are in the mass spectrum of 1,2-dibromoethane, assuming the only isotopes present are H1, C12, Br79 and Br81. So we only have to write molecular or parent ion peaks. We have 2 bromine isotopes, so first we will draw the displayed formulas of all possible molecules. One peak would be for 79 to 79, one peak would be for 81 to 81, and a peak with twice the abundance for 79 to 81 and 81 to 79. since they have the same mass but twice the probability. So totally we will have 3 peaks. The other peaks for carbon and hydrogen will not be different because in the question it stated there is only one isotope for carbon and hydrogen. A student sketched the mass spectrum of chlorine gas, which contains 75% of the Cl35 isotope and 25% of the Cl37 isotope. Identify and correct the 2 errors made by the student in the sketch. The monoatomic ion peaks are of the same abundance, but Cl35 has 3 times the abundance than Cl37, so it should be thrice the height. And there is no peak at 72 for 35 to 37 Cl and 37 to 35 Cl. There should be a peak at 72, ratio should be 9 to 6 to 1 for the diatomic molecular peaks. Alright, I hope you understand. Thank you, bye bye. Feel free to ask any question in the comments.